In science, we sometimes have to deal with extremely large and extremely small numbers. These numbers are inconveniently small and large because they just don't fit in the display of even a scientific calculator. Now, while you might be able to get a number with 20 or 30 digits into a graphing calculator display, that doesn't make it convenient to deal with. In fact, as soon as a number has so many zeros that you have to physically count how many zeros are there to determine the number of zeros that are present, it's a number that really belongs in scientific or exponential notation. And here's a great example of a number like that. This is Avogadro's number, very important to the calculations we make in chemistry. 602 with 21 zeros. Now again, you could get this number into a graphing calculator, but it would be very inconvenient to do that. If this were the answer to a problem that was being displayed in a graphing calculator, you would have to sit there and physically count the number of zeros. That makes it a good candidate for scientific notation. So in red, what you're looking at is what's called an ordinary notation number. Those are the normal ways that you've represented numbers your entire life. But here's another way of representing the same number. 6.02 times 10 to the 23rd. This number is in scientific notation. The size of these two numbers is exactly the same. In fact, these two numbers are totally equivalent in every conceivable way. But obviously there are some differences in how they're expressed. So in the scientific notation number, there's three distinct features that are present. So the first thing that you have is this number out front that I'm putting inside this purple box. Now this number here is known as the mantissa. And by definition, the mantissa is always a number between 1 and 10, except it could never actually be 10. It can approach 10, but it would never actually be a 10. Then you have the times 10 component, and then in this purple circle, the exponent. Now in this case, you'll notice that the exponent is a positive number, and positive exponents represent large numbers. If the exponent were a negative value, that would indicate that the original ordinary number was a small number. Now there's several things that you must be able to do with scientific notation numbers. The first is to be able to take an ordinary number and convert it into scientific notation. So for that, we're going to look at the first set of practice problems. And you'll notice there's a set of numbers here that are written out in ordinary notation. I want to convert them to scientific notation. Now I agree that some of these numbers are not good candidates for scientific notation, but the directions here are to please change each of these ordinary notation numbers into scientific notation numbers. So we'll do number 1 together. In problem number 1, we have the number 67,000. Well, the first thing I need to do is to reposition the decimal point. Now, there is no visible decimal point here, so we all understand that the decimal point is currently in this location here. I want to move the decimal point, so I create a number between 1 and 10. So if I move the decimal point between the 6 and the 7, that will give me the mantissa of 6.7. And that would be the proper place to put it. Then, of course, you have the times 10 feature, and now all that's missing is the exponent. Well, we know the exponent will be positive in this case because we're dealing with a large number. The size of the exponent, though, is equal to the number of places that the decimal point has been moved. Now, because we already know it's a positive value, we don't need to concern ourselves with which direction we're moving the decimal point. That's already here by knowing that the exponent is going to be positive. So I could start here and count back 1, 2, 3, 4, or I could have started on this side and counted forward 2, 3, 4. Either way, I get that it's 6.7 times 10 to the 4. So that ordinary number has now been converted to a scientific notation number. Now, problem 3 is a better candidate for scientific notation, but again, especially with the commas there, I don't think anyone needs to count up how many zeros are present to determine how many zeros are present. One quick look and right away you should know that there's 7 zeros there. But once you pass 7 zeros or so, you're really getting into a realm where scientific notation is going to be making more and more sense. So like the first problem, there's no visible decimal point, but it's understood to be here. So we're going to move it so it's between the 8 and the 9. And that gives us a mantissa of 8.9. Now if I had moved the decimal point to out front here, that would have given us a number of 0.89, and that would not have made the mantissa between 1 and 10, so that would have been a bad choice. If we put it here after the 9, that would have given us the number 89, and that's too large for a mantissa, so that would have been an incorrect location as well. We know times 10 is there. We know the exponent is going to be positive because we're dealing with a large number. All that's left is the number of places that we've moved the decimal point. So let's just count out how many places that is. 1, 2, 3, 4, 5, 6, 7, 8. And this exponent is an 8. 8.9 times 10 to the 8. Now what if you're dealing with a small number? So this would be a number less than 1. So problem number 5 is just one of these cases. Now the difference here is that we're still going to have the times 10, but the exponent is going to be a negative exponent. There is a decimal point in numbers like this, right? It's already printed on the page, but like before, we have to move the decimal point to create the mantissa that's between 1 and 10. So if we move it between the 4 and the 5, that'll give us 4.5. All that remains is to figure out the number of places that we've moved the decimal point. 1, 2, 3, 4, 5, 6. This is 4.5 times 10 to the negative 6. Now what I suggest you do is pause the video, solve the rest of the problems, or as many as you think you need to solve to gain mastery here, and check the answers. Please always check the answers. The answers are available at the end of this set of practice problems. If you can get the right answers, then you're probably good, and then you would move on to the next section. Now in the next section, you're going to go the other way. Here you're starting in scientific notation, and you have to take the number out of scientific notation and make it an ordinary notation number. Now there are ways for your scientific calculator to do this automatically for you, but that's not going to work if the exponent is just too large a value. So you have to be able to manually do this yourself. So 8.2 times 10 to the third. So we're starting with 8.2, and we're going to move the decimal point 3 places such that we make the number larger because the exponent is again a positive value. So 1, 2, 3 places where it's understood that these missing digits must be zeros. So the original ordinary notation number was 8,200. 1.5 times 10 to the minus 6. So now in this case, we're going to go the other way. We're starting with 1.5, but because the exponent is a negative value, we know that the original number was a very small number. So this time we're going to move the decimal point 6 places in the opposite direction. 1, 2, 3, 4, 5, 6. There's our decimal point, and of course all these missing digits are 0, and it is customary to put that 0 before the decimal place. So that's a total of 6 zeros that we wrote, and the 1 and the 5. All right, folks, good luck. Try this section, check the answers. When you feel you've got it, on to the last section. Okay, starting with problem 21, you're going to do some simple calculations, multiplying and dividing two numbers. And these are all ordinary numbers that you're going to multiply and divide. The answer might fit in the display of the calculator, or it might be so large that it does not fit in the calculator, and your calculator will resort to scientific notation. Whatever the case, you have to decide how to present the number in scientific notation. So I understand, again, that some of these answers might be as simple as, say, 5, and you could just write 5 on the page. That's not the directions here, folks. The point of all of this is to practice scientific notation. So even if the answer works out to be the ordinary number 5, you have to figure out how to represent that in scientific notation. And there is one other thing that this sheet is about, but I'll talk more about that at the end. So in problem 21, just take your calculator and punch in 25,000 times 16,000. And my calculator leaves this as an ordinary number, which is really inconvenient. So when I do this, when I draw a rectangular box, this is me representing the display of the calculator. Now what I see there is definitely a 4. Now it's not obvious to me how many zeros there are, so I have to take a moment and carefully count them out. 1, 2, 3, 4, 5, 6, 7, 8. All right. 1, 2, 3, 4. 1, 2, 3. There we go. So that's what it looks like in my calculator display. So while I could leave this as an ordinary number, I'm asking you to practice scientific notation, please. So write this as a scientific notation number. So that's definitely going to be 4 times 10 to some positive exponent. 1, 2, 3, 4, 5, 6, 7, 8. So this is 4 times 10 to the 8th. Now some of your calculators might have already put that answer in scientific notation, and that largely depends on your calculator. Different calculators are set to resort to scientific notation earlier than others. On many scientific calculators, you can also set where this point is, right? But that's typically something that most students don't fiddle with. All right, so you're just going to keep doing this. You're going to do the indicated operation. You're going to get to the answer. If it's in scientific notation, just write it down. If it's not in scientific notation, please convert it to scientific notation. And as you go through every couple problems, check those answers. Be sure that you're doing things correctly, folks. All right? What I would not want you to do is do something incorrectly, do it again and again and again, get a lot of reinforcement, and then check the answers and find out that you're not doing it correctly. This is why all the answers are available to you, both the practice problems that I wrote, right, and every single textbook problem that I offered you. So it's very, very important to be sure that you're doing things correctly so that you can really habituate your brain to doing things in that method that brings you to the right answer. You don't want to reinforce the improper sequence of steps. All right, so the last thing that this sheet is about will be demonstrated by this next problem, 23. 575,000 divided by 8,000. Now, my calculator shows this as an answer. Now, 71.875. How will I represent that in scientific notation? Well, there's a lot of variation when students put an answer like this in scientific notation. And if we were face-to-face, this really would have been perfect because I would have given you a few minutes to do a couple problems, and then I would walk around the room and see what people had for a problem like this, and there'd be so many different choices, right? So here's an example of the different answers that I would see. So that might be one of them. Here's another answer that I would see. Here's another. Here's another. And maybe someone would also put that. So all of these are very, very similar. right? I mean, they're all just examples of different degrees of rounding. Now, you've spent, most of you, if not all of you, years and years and years making calculations and rounding those calculations. It's just something typical that we do. But in a class like this, in a technical class where there's lots of specific rules in terms of how we do things, all of a sudden, many of you would be concerned if your rounding was correct or not. And frankly, this problem is here to put you in that sort of questioning state. Which of these is the right answer? So maybe one of you would have put this down, and then the person working next to you put this down. And I ask you, once you're done with a couple problems, to lean over to the person next to you and sort of consult and check to see if you have the same answer. And now the concern becomes, well, wait a minute, I've got the green answer, she's got that purple answer, who's got the right answer? And then you look up on the screen where I post the answers, and what you find there is that I've identified this is the most correct answer. And now both of you are concerned. So the issue with rounding is a real issue in a technical class like ours, right? In a math-based, measurement-based class like chemistry or physics for that matter. And we're going to have some elaborate discussions on this when we talk about sig figs in the next topic. So for right now, the exact rounding really doesn't matter. This problem is here to show you why we all need a set of rules for rounding, so that every single person can get exactly the same answer to the same problem. Without those rules, you might have this answer, another person has this answer, another person has this answer, this answer, this answer, and then we get bogged down with discussions of whose answer is right. Now, why is my answer the right answer? Because I'm following that set of rules that we have not yet discussed. On this page, though, no one needs to worry about that. I never ask you to do something for which we have not first provided instruction. This is about scientific notation, not about rounding, right? So as you check the answers and you see small differences between your answer and my answer, it's just because of a rounding issue. Something we'll resolve in the next set of topics. All right, everybody, good luck.